We will now focus on learning the basics of how to identify and interpret the main types of igneous rocks. This one right here is exposed along the Agua Fria River north of Phoenix in central Arizona. It is what we call a granodiorite, and it is Paleoproterozoic in age, roughly 1740 million years old, and is one of the oldest rocks in Arizona. After a magma forms, it will initially rise because of its greater buoyancy, just like the red blob in this lava lamp. The magma will eventually begin to cool and crystallization will begin. If a magma cools and crystallizes at depth, it will become an igneous intrusion. This is an example here, with the Swiss Army knife for scale, of magma that cooled somewhere at depth, fairly slowly allowing large crystals to form. This is something called a pegmatite intrusion. If a magma migrates to the surface and erupts as lava, it will become an igneous extrusion. The Mount Rainier volcano is an example. By the way, lava lamp is what people call them, but I think magma lamp is more accurate. Here is Mount Rainier, also known as Tahoma or Tacoma. At 14,417 feet in height, Rainier is an active stratovolcano that last erupted in the 19th century. The summit area includes over 20 major glaciers, and due to the large amounts of accumulated snow and ice, any significant eruption will likely produce dangerous lahars and mudflows that will threaten the populated Tacoma area to the northwest. Mount Rainier is one of many ring of fire volcanoes in the Cascade Range, like Mount Baker to the north or Mount St. Helens to the south. Just remember, these represent the volcanic culmination of magmatic processes that began deep within the earth. And although unseen to us, any active volcano that you see is connected to subterranean magma chambers below them. A solid rock formed from the crystallization of magma or lava is called an igneous rock, and can be classified and interpreted based on its composition and texture. The types of minerals in an igneous rock determine its composition. The composition of an igneous rock can tell us about what was originally melted, the magma's source area, and any differentiation processes like crystal fractionation, magma mixing, crustal assimilation, etc., that may have altered the magma's original composition. In igneous rocks, texture refers to the size and arrangement of crystals and other structures in the rock. The texture of an igneous rock can tell us about where and how the magma cooled and crystallized and even erupted. Thus, we can learn a lot from observing and interpreting the mineralogy and texture of an igneous rock. For instance, the rock here is composed of mostly large, light-colored mineral crystals. This coarse-grained texture suggests that the magma cooled rather slowly within a magma chamber at depth. The light-colored mineralogy, we call this composition Felsic, suggests that the source of the magma was probably in the crust, crustal melting. This rock is composed of much smaller crystals. This fine-grained texture suggests that the magma cooled rather quickly on the surface. Again, the light-colored felsic mineralogy suggests that the source of the magma was probably in the crust. This is a rock identification chart for igneous rocks, and includes the major compositions and textures, as well as comments and various interpretations. To name an igneous rock, we need to be able to identify its composition and texture. For example, if a rock is composed of mostly light-colored minerals, then its composition is said to be felsic. If the crystals are relatively large, like between 0.5 centimeter and 2 centimeters, then its texture is coarse-grained. Thus, an igneous rock with a felsic composition and a coarse-grained texture is called granite. In another example, if a rock is composed of mostly light-colored minerals, or is generally light in color, then its composition is felsic. If the crystals are very small, say less than 1 millimeter in average size, then its texture is fine-grained. Thus, an igneous rock with a felsic composition and a fine-grained texture is called rhyolite. Note that this rock has the same composition as the previous one. Both granite and rhyolite have a felsic composition, which means that they could have originated from melting of the same source rock, possibly even from the same batch of magma. However, they each have distinctive textures. The granite had large crystals and coarse-grained texture. The rhyolite has very small crystals and fine-grained texture. And that tells us even if these rocks were created from the same magma, they experience different cooling and possibly eruption conditions since their formation. Let's look more closely at the main igneous compositions: felsic, intermediate, mafic, and ultramafic. We'll begin with mafic and ultramafic. Mafic compositions are those that are relatively rich in iron, magnesium, and/or calcium, and are correspondingly poor in other elements like silicon, sodium, potassium, aluminum, etc. This simplified diagrammatic magma chamber shows a silicate magma, and so it has oxygen and silicon. Notice the silica tetrahedra form there with 4 oxygens around the silicon. Anyway, in a mafic silicate magma, you always have silicon and oxygen, but you have an abundance of iron, magnesium, and/or calcium, and it's relatively lacking in other elements like sodium, aluminum, etc. Ultramafic magmas have even higher percentages of iron and magnesium and calcium, and lower amounts of silicon, sodium, potassium, etc. Mafic magmas form from the partial melting of ultramafic rocks in the mantle. This typically occurs at intraplate hotspots and divergent margins, whether they are oceanic divergent, like mid-ocean ridges, or continental divergent, like continental rifts. Upon cooling, mafic magmas crystallize iron, magnesium, and/or calcium-rich minerals in various proportions, including olivine, pyroxene, and calcium-rich plagioclase feldspar. These minerals compose most mafic igneous rocks, like basalt and gabbro. Ultramafic magmas produce even higher percentages of these minerals, especially olivine and pyroxene. Common mafic rock types include basalt, scoria, diabase, and gabbro. Note in the identification chart, the mafic compositions are also described as rocks with 40 to 90% dark minerals. So a rock having at least 40% dark minerals up to 90% is considered mafic. Certainly when you look at basalt and scoria, even gabbro, these are dark-colored rocks. Common ultramafic rock types include pyridotite and pyroxenite. Note that ultramafic rocks have more than 90% dark minerals. Certainly pyroxenite is very dark rock, but pyridotite is loaded with the green mineral olivine, which you wouldn't really consider dark. Well, green olivine is considered a dark-colored mineral because its composition is basically iron, magnesium, silicon, and oxygen, and that's about it. It's an iron-magnesium silicate, and so it's about one of the most iron and magnesium-rich minerals that you can find. Kimberlite is a rare ultramafic intrusive rock that is known to host diamonds. And Pegmatite is an extremely rare ultramafic volcanic rock. Mafic igneous rocks like basalt and gabbro are abundant in the oceanic crust, whereas ultramafic rocks like pyridotite are a major rock type in the mantle. In fact, as mantle peridotite melts, it produces a liquid that is mafic in composition, which eventually forms basalt and gabbro of the oceanic crust. Felsic compositions are those that are relatively poor in iron, magnesium, and calcium, but correspondingly rich in other elements like silicon, sodium, potassium, aluminum, etc. Here in our magma balloon example, we can see that felsic magmas are silicate magmas, so there's silicon and oxygen. But in these type of magmas, there's typically an abundance of silicon and oxygen, so even more. And then add to that sodium, potassium, aluminum, other elements. Felsic magmas form from the partial melting of source rocks in the continental crust at convergent margins and continental rifts. Upon cooling, felsic magmas crystallize iron, magnesium, and/or calcium pore minerals in various proportions, including quartz, potassium feldspar, sodium-rich plagioclase feldspar, and different types of mica. These minerals compose most felsic igneous rocks, like rhyolite and granite. Common felsic igneous rocks, those with less than 15% dark-colored minerals, include rhyolite, dacite, pumice, obsidian, granite, and granitic pegmatite. Felsic rocks like rhyolite, pumice, and granite are abundant in Earth's continental crust. Intermediate compositions are those between mafic and felsic, and include more moderate amounts of the elements found in mafic and felsic magmas. In our magma diagram here, intermediate magmas are silicate magmas, so include some amount of silicon and oxygen, slightly more than mafic magmas, but less than felsic ones. And there might be a mixture of elements found in both mafic and felsic magmas, including silicon, iron, sodium or magnesium, potassium or calcium. Intermediate magmas form by hydrous or wet melting of the mantle and crust, and also by the mixing of felsic and mafic magmas. This typically occurs at convergent subduction zone boundaries, whether it's ocean-ocean convergent or ocean-continent convergent. Upon cooling, intermediate magmas typically crystallize minerals like plagioclase feldspar and amphibole. These minerals are abundant in most intermediate igneous rocks, like andesite and diorite. Common intermediate rock types include andesite, pumice, and diorite. Note that intermediate compositions have between 15 and 40% dark-colored minerals. So, in rocks that have large crystals that can be seen with the naked eye, it lends a salt and pepper texture to it, light and dark. In rocks with much finer grained crystals, where they're too small to be individually seen with the naked eye, intermediate compositions are typically more gray in color. But color can be highly variable. These are just generalizations. Intermediate rocks, like andesite and diorite, are also abundant in Earth's continental crust, as well as in island arcs. Now let's look at some important igneous textures. Remember, rock textures describe the size and arrangement of crystals and other structures in a rock. Igneous rocks with pegmatitic texture have huge crystals, typically greater than 2 centimeters in size, and rarely even meters in size. This texture forms as a hydrous or water-rich magma cools slowly at depth, so it's an intrusive texture. This texture is also more common in felsic compositions. One example is granitic pegmatite, like the one shown here, exposed along Tuna Creek in the Grand Canyon. You can see the reddish-colored potassium feldspar, white quartz, and silvery plates of muscovite mica huge crystals there. Coarse-grained textures include large crystals ranging from 2 centimeters to about half a centimeter in size. This texture is also known as phaneritic, from the Greek phaneros, which means visible, and you can see most of the crystals in this kind of texture with the unaided eye. Coarse-grained textures are formed as magma cools slowly at depth, so this is another intrusive igneous texture. And examples of coarse-grained rocks include granite, granodiorite, diorite, gabbro, peridotite, pyroxenite, etc. The large crystals in the granite shown at right can also be viewed in thin section, where we cut the rock to a very thin section, about 30 microns thick, so you can actually shine light through it and look at it under a special microscope called a petrographic microscope. And the image at bottom shows what these minerals look like under the microscope, with the light-colored quartz, the very distinctive patterned alkali feldspar, and the brightly colored dark mineral biotite. Fine-grained textures include small crystals less than a millimeter in size. This texture is also known as aphanitic, from the Greek aphan, which means invisible, and you cannot see most of the crystals in this kind of texture with the unaided eye. Fine-grained textures are formed as magma cools quickly on the surface, so this is an extrusive igneous texture. Examples of fine-grained igneous rocks include rhyolite, dacite, andesite, basalt, etc. Porphyritic textures include both big and small crystals. Formation of this texture involves at least 2 stages of cooling, with slow cooling at depth, forming the large crystals, followed by faster cooling at or near the surface to form the smaller crystals. This is a very common volcanic texture, and the word porphyritic is typically used as an adjective. Examples of porphyritic rocks include porphyritic rhyolite, porphyritic andesite, and porphyritic basalt. The large crystals in these rocks are known as phenocrysts, and the smaller crystals that surround them form the ground mass or matrix. So in this hand sample, you can see large crystals of feldspar, the lighter colored crystals of feldspar, surrounded by a gray ground mass, which you can't see crystals. And so 2 different crystal sizes representing 2 stages of cooling. Looking at this rock in thin section, you can see the relatively large feldspar phenocryst there on the right and towards the top. The dark colored crystal at the upper left is also a feldspar. It's just the way the polarized light works with a microscope. And then all the fine-grained crystals in between is the ground mass, and those are probably crystals of feldspar and amphibole or other minerals. A porphyry is a rock that has a range of typically large phenocryst sizes. Glassy textures have very few crystals, if any, and are formed by ultra-fast cooling or quenching on the surface. Rocks with glassy textures can have any composition and can be referred to in general as volcanic glass. But obsidian is the most famous and occurs in several different varieties, all of which are felsic in composition. Vesicular textures have holes, or vesicles, that are created as gas bubbles form and try to escape a magma, but are trapped during solidification. And this occurs usually at or near the surface. So, vesicular textures are, again, an extrusive texture. Examples of rocks with vesicular textures include pumice and scoria. Scoria typically has greater than 30% vesicles. The word vesicular is also used as an adjective for any volcanic rock with less than 30% vesicles, like vesicular rhyolite or vesicular basalt. Vesicles are actually very common in volcanic rocks, whether it's a few percent or 5%. We typically don't call them vesicular necessarily unless they have a little bit higher percentage. Pyroclastic textures are composed of pieces of rock of different sizes and form from explosive volcanic eruptions. Fragments range in size from large blocks and bombs, greater than 64 millimeters in size, to gravel-sized lapilli, 2 to 64 millimeters in size, to fine-grained ash, less than 2 millimeters in size. Rocks having pyroclastic textures include pyroclastic breccia, agglomerate, lapilli tuff, and ash tuff. In general, the size of the fragments can be related to the explosivity of the eruption that created them. For example, smaller eruptions, like with cinder cones, erupt a lot of blocks, bombs, and lapilli, which mostly fall back around the vent area. Whereas larger volume eruptions, like with major calderas, erupt significant amounts of fine-grained ash, which is sent high into the atmosphere, where it is then carried downwind for long distances, sometimes even around the world. Well, that's all for now. Till next time.